Okay, I'm ready when you want, I
Excellent.
can start.
So maybe let me say a few words at the beginning. Actually, it's a long story of our collaboration with Torino Politecnico. And I remember that it was more than 20 years ago when I first visited Torino, and it was a real pleasure not only to see this beautiful city, but also to meet this team of researchers guided with Roberto Tempo, and also to meet Fabrizio, Giuseppe Calafiore, and many others. And I am very glad that our collaboration continued so long. And for instance, Roberto visited Moscow several times and gave lectures here, and we co-authored with many people, and our collaborations continues. And now, for instance, I know that Fabrizio, you are in close touch with Pavel, and your paper is prepared, very nice paper, new paper, and so on. So we are happy that you can give us this lecture, and actually it's new, maybe a new direction for research for us. So please, Fabrizio, you are welcome.
So, Boris, thanks a lot. When Pavel invited me, I was very, very happy. Said, I mean, as I was saying before, it is like seeing old friends. I mean, I see many faces that I met in person in Moscow. The only sad thing, I would really like to be there. I would really like to be in Moscow and have this seminar at the institute, because I had beautiful moments during my visits. I had I would say 3 visits if I also add Boris Fest for your birthday, and all of them were so nice, both technically, because we had a lot of discussions, a lot of ideas, and I remember writing notes in the Pushkin Cafe. That was one of the best days of my career, and so I'm very happy to be with you. And thanks again, and hopefully next time I will be there in person.
Yeah,
Really,
we do hope that everything will be repeated.
yeah, we all look forward to that. So, do you see my slides?
Yes.
Okay,
Yes.
perfect.
Yeah.
So, I decided to give an overview on our recent works on, again, randomized algorithms, which is one of the main research topics, and also the main research collaboration between myself and the Russian guys, and to present you some new results on the approximation of change constraint sets. And the methods developed are based on a technique that we call probabilistic scaling. And the idea is that we have uncertainty in an optimization problem. I don't have to convince you that uncertainty is everywhere. Plinius the Old used to say, solum certum nil esse certi, which means the only certain thing is that nothing is certain. So uncertainty is everywhere. And when you deal with optimization problems nowadays, where the optimization problems are taken from real world, we want to solve real world problems, we have an imperfect knowledge of the design environment, so we have uncertainty. And this is a key issue. And we all come from robust control. in robust control, this is the classical mu delta configuration. You have uncertainty and you want to design a controller that is guaranteed for all possible values of uncertainty. And this is a worst case scenario. You're designing your controller for the worst case uncertainty, and this is conservative. We know that. So this is, if you want, a pessimistic way of dealing with the problem. And on the other side, you can have an optimistic way, saying that we want to guarantee something in probability. And this allows to introduce the ideas and the concept of this talk, which I would quote a sentence that Roberto Tempo liked a lot. We put it in our paper that says, in our book, that says, you shouldn't assume the worst case scenario. It's emotionally draining and probably it will never happen. So let's be optimistic and look for probabilistic solutions. So solutions which in system control means accepting some risk, in optimization means accepting some risk that your optimal value isn't good in the face of the center. And the tools that we have been using and we have been promoting also with Pavel, with Boris, and with Andrei, so I don't have to convince you, are randomized algorithms, which are based on a random toss of a coin. And the idea of Monte Carlo-like algorithms is that you do random choice and you have a result that can be wrong. So you can have to accept a probability of failure. And when we talk to system and control, when we talk about random variables, we talk about samples of the uncertainty, observation of the uncertainties. So let's focus on optimization. So we want to optimize something in the presence of uncertainty. Again, we can have the pessimistic view, where you want to solve a robust optimization problem. And I want just to see the time. I don't see the time. Oh, okay, it's there. And so you want to minimize some cost function subject to an uncertain constraint, where here for notation, theta for all the talk is the design variable that you want to minimize for. And W is some uncertainty that is lying in some uncertain set W, big W. And so the robust optimization is you want to minimize some function subject to the fact that the constraints are satisfied for all possible value of W. On the other hand, you can have the change, what is called change constraint optimization, where you want to minimize with respect to the fact that the probability of constraint, okay, this is wrong, there should be of constraint violation, so there is not less than equal than 0, is small enough. So you want to guarantee that the probability of violation, the violation probability, is more than a quantity epsilon. And so this is where I will concentrate our talk, my talk today. And to make things simple, and this is just to make things simple, all I will present today can be extended to the general framework, but let's say that we have linear inequalities. So we have a matrix F with row F1, Fn, which are dependent of the uncertainty, vector G whose elements depend on the uncertainty, and we have this uncertain linear inequality. And so what happens is that for every value of omega, you have a linear inequality. So you have an infinite number of linear inequalities, one for every possible value of omega, of W, if W is as a dense support. So these are the inequality. I define the probability of violation. If I have a design theta, a given design theta, the probability of violation is the probability measured over the set W. So I have to assume that I have some probability measure lying with support W, big W. And the probability of violation of a given design is exactly the probability that for that design, the constraint will be violated. So it's a probability measured in terms of W. And what I will focus on this lecture is this set that I call X epsilon, is the set of theta, so in the design variable, for which the probability is less than or equal than epsilon. So I'm looking at the design set, at the thetas, the change constraint set is the set of all thetas for which the violation is less than or equal than epsilon. And here, this is important. Here I'm considering this written like this. So writing that theta belongs to the set means that we are imposing what is called a joint change constraint, because we are measuring the probability of the all linear inequality, FQ less than or equal than G, so the all linear inequality. This is different of assuming that for every value of L, these linear inequalities, scalar linear inequalities are satisfied. So we are considering joint change constraint, which, by the way, is a harder problem than the individual change constraint. And so this set. Yes.
May I ask a question? By proper choice of epsilon L, can you reduce your problem to the problem with the individual constraints?
Yeah, there is some, I mean, you can choose epsilon L in such a way that this implies this, or vice versa, but you cannot write them in an equivalent form.
Yeah.
So you can choose epsilon L small enough such that if this is verified, this is verified, or vice versa, you can choose epsilon in such a way that if this is verified, this is verified. But they are different, different problems. And so my goal is will be to find approximations of directly approximation of this set. So I will focus on the change constraint set. So how does this set look like? We all know that this set in general can be non-convex. And so we tried a very stupid example of a 3x3 F matrix, and with some random elements, I mean, this is just an example, numerical example, and you see that you see this set for different value of epsilon. And so the larger is epsilon, the larger is the set, because you're logging more violation. And you see really that the set is non-convex. So you see this guy here is really non-convex. Here you see a little bit of non-convexity. And you see also this nice behavior, which is somehow called ultimate convexity. If epsilon becomes very, very small, the set becomes convex. And this has something to do with some work that Boris also did on the fact that for small balls, you have convex properties. So this is, but here just to show you graphically what is the quantity that we want to approximate, which is this strange set in the change in the design space. And clearly, if you do this, if you have a cost function, the problem of change constraint optimization is to minimize the J in such a way that the theta belongs to this change constraint set. This is the change constraint optimization. So is this a hard problem? in general, yes, you can find convex cases. For instance, if Q is Gaussian, and here this is no slide, Fsq was already linear. So when omega is Gaussian, sorry, or you can have robust approximation. So you can find approximations which relax this problem into a robust problem. And starting from the robust counterpart of Verzekas, approaches based on CVAR. You can have semi-definite programming approximation. There are recent works by Costantino Lagoa where he uses moment-based approaches to approximate this set in a deterministic way. So you find what you will do, you will find a set which is guaranteed to be inside this set. So if you minimize with respect to this set, you will guarantee the right probability that the solution doesn't violate your probability of violation. And what we will discuss is sample-based methods. This is a picture that I took from a nice survey published in Annual Reviews of Control of all change constraint optimization method. You see that it's really an old problem formulated by Chance in the 50s, and you have different approaches. You see here approaches based on special cases in convexity. You have the work of Shapiro. There is very interesting work from Precopa, Lagoa, Calafiore. This is special cases. On the other side, you have robust counterpart, and you have again Russians, Nemirovsky, Shapiro, Bental and Nemirovsky, Bersimas. And here you have method based on sampling. On one side, you have the scenario approach. We will discuss that. And on the other side, you have the sample average approach. So two different approaches. And our approach is somewhere here. If you want to place it, is somewhere here. So let's...
Pavel, yeah, please. Pavel, interrupt.
Yeah, please ask questions.
Yeah, sorry. So,
let's make it as I was there, so I feel less alone in the office.
Okay. So the question is, why are you looking for an inner approximation? Because you are minimizing something over a set. If you approximate it from inside, then your minimum might be even only bigger.
I'm approximating from the inside because I want to guarantee that my solution is inside the set. My solution. So this is the set where the solution is good, where the probability is less than epsilon. So I want to stay inside the set.
Well, but the value of the cost, what about it?
The value of the cost will be larger because I'm minimizing, which is okay. I mean, it's a conservative approach. If you stay inside, I mean, what people in robustness do, they stay inside, they try to stay inside, and they get a conservative answer.
Okay.
If I stayed outside, I could end up selecting, I will, because of, we end up selecting a design which doesn't guarantee the required probability.
Yeah, otherwise you cannot guarantee the probability. Yeah. Okay, I got it.
And you will have a smaller minimum, you're right, but you will not guarantee. So what you can do is apply the scenario. Scenario is just that. Scenario, I don't have to explain scenario to you, but I take n samples and I evaluate these linear inequalities on n samples. So I will have n linear inequalities. And then I solve the scenario problem, where instead, where I solve this problem only constrained to the sampled scenarios. I mean, samples vary of the uncertainty. these samples can be either real samples or observation on your phenomena that you use to, as Marco Campi likes to say, that this scenario approach indeed is a data-based approach. So if you have data, if you have observations, you can use that to have an answer. And look here, I'm not comparing with the robust approach, I'm comparing with the change constraint approach. So this approach guarantees that if you take n such that this is the classical binomial, I forgot to put the formula, but this is the classical binomial. And if I choose n in such a way, for a given choice of n, the probability that the violation will be larger than epsilon can be bounded by this binomial. You can invert this formula and you can find the number of samples that guarantees that the probability of violation is less than epsilon. This is scenario, and what we are doing here is just taking n samples. You see here n samples, and basically we are constructing this set xn, and then we are optimizing, and we guarantee that this point, the optimal point, is a point that belongs to the setting, basically. So this is scenario. Are we happy with this? Depends. I mean, if the problem is really to optimize, of course, you have to assume that J is convex, you have to make some assumption on the problem, on the generality, and so on and so forth. But what you have here is that this point belongs to the set. Actually, the key observation that I want to make here is that this property, if you apply scenario, holds only for the optimal point. So you can say basically that this optimal point belongs to the set x epsilon. Sorry, this should be x epsilon. The optimal point belongs to the change constraint set of parameter epsilon. Can we say something on the set itself? I mean, on this approximation? Actually not. We cannot say anything about this approximation. So the question remains, is this approximation, so if I take n inequalities, I construct this blue set, is this approximation a good approximation of the true change constraint set? If we apply scenario, we cannot do that. So this is the problem that, so it took me 20 minutes to introduce the problem, but this is exactly the problem I want to solve. Given the set of linear inequalities and the violation parameter epsilon, I want to find a linear approximation of the set XC, an approximation which tries to stay inside, that is simple enough and easily computable. The first thing I can do is, that we did, this is some work that we did with Roberto, Matthias Lorenzen, who is a student of Frank Gower, so the four of us, is just applied learning theory bound. So let's say that this x epsilon is the true set, the true change constraint set, which we don't know, but we know it's ugly and it has this very ugly shape. We take this approximation taking n samples, and we proved very simply by applying learning theory bounds that if you take this number of samples, this set will be an inner approximation of this one with large probability. So the probability that this set is inside this one, you can have it larger than what you want. And of course, you see here, this is almost inside. There are regions that are not inside. And what we are saying basically is that these regions, let me see, maybe I can have a laser pointer. Okay, these regions are very small. So the probability of this region is really small. And we did that, and we applied this to stochastic MPC. In stochastic MPC, it's important the fact that you can apply a scenario, but if you apply scenario, you have to do it online. if you approximate the whole feasible set offline, you can do all the computation offline. And this is the powerful things of these two papers. I don't tell you all the approach, but the idea is that you have a system with uncertainty here, here, and here. I mean, in A, B, and you can have noise, you can have everything. And we apply this to the problem of rendezvous and docking of satellites. So the problem is that this is the target satellite. This is the chaser, what is called the chaser. The chaser should reach the target, stay inside this feasible region. You see, in space, when they get close, you have to approach the chaser have to approach the target in a given region in order to have a locking of the two things. And this should be completely automated. And this is exactly what we tried. And so we did that either both experimentally and both in simulation and experimentally in collaboration with NPS, National Naval Postgraduate School of Monterey, where we have this very, very nice setup. They have a marble granite monolith. These things weighs. I mean, they had to have a special basement to build this thing. This is completely flat and polished. These are mock-ups of real satellites. They have the same hardware on board, and they have some air pressure that is pushing down so that the friction goes to zero. So if you touch them, they will move, and you have to stop them, because if they break, you're breaking a lot of money. And we tried these, as I said, both experimentally. These are simulations, and these are real experiments. You see, the only difference here is that when you reach this region, there is a magnet, and they lock together. And we were able to have that work. Let me see. If I have the laser pointer, it doesn't work. Okay. I don't know if you hear the noise. Do you hear the noise?
Yeah.
So the noise, every time you see a light, is a thruster that is pushing. Actually, this is twice the speed. These things are going very, very slow. But they worked, and the important thing here is that being able to directly approximate the change constraint set allowed us to have all the computation done offline. So offline, you're doing sampling, you are constructing your set, and then online, you're just using this approximation. But all the computation is offline. So this is the nice thing. All the heavy computation are offline. You end up with a lot of linear inequality. And when I say a lot, it's really a lot. And then you prune them, and you try to construct something which is feasible. We proved that you can do that on a real experiment, but still, I mean, if I tell you the number in this, if you have, let's say, 5 states to input, prediction horizon 10, reasonable values of epsilon and delta. Remember, delta is under the logarithm, so you can choose it very, very small. You need 1.6 million linear inequalities. So my student, who now she's working from me, did a lot of experiments. I mean, had to work a lot, and the computer was working for days to prune these 1.6 million. And to most of them are redundant, because you are, but it took a lot. So the idea is, the motivation here is that, can we have something more tunable? So we want to approximate this set. We know this set is very strange, and we want to approximate it somehow. And so the idea, and this is the motivation of the probabilistic scaling approach, which we have been working again with Matthias. with Teodoro Alamo, that most of you know. Martina Mammarella is my collaborator, and Victor Mirasierra is working with Teodoro. So what is the idea? We have the set. This is the set, the change constraint set. We take a family of approximators, and let's say that the family approximator is defined this way: is a center, this is the center, and a shape. Let's say here it's a pentagon. It can be a shape that you decide. And then you have this parameter gamma, with which you can either inflate the set or deflate the set. So you start with an initial set and either inflate it or deflate it in such a way that its probability of violation will be the one that you want. So this is the idea. You start with this family of sets. Here, I'm not telling you how to construct this family of sets. This will come up later, but here, this is the idea. You have this family of sets, center plus shape. Imagine the classical ellipsoid. You have the center and you have the ellipsoid that you can inflate or deflate. In that case, you have one parameter. Usually, with one parameter, you can inflate and deflate the set. In the case of ellipsoid, it's the radius, basically. How can we decide the right side of the set? Again, we use sampling. So we take n-gamma samples. And based on n-gamma samples, I will give you a procedure that allows you to construct this scalar gamma, so the radius, the scaling, what we call the scaling, the probabilistic scaling, in such a way that the final set will be a good approximation. What I mean by the good approximation, I mean that it stays in x epsilon with probability greater than 1 minus delta. How can we do this? Okay, the tool is what we call the scaling factor, which is simply this thing. Consider one single value of omega, so one sample. When you have one sample, you will have an hyperplane and a region where the constraint is violated and a region where the constraint is not violated. And you can construct the gamma corresponding to this set as the largest value of gamma, such that the set doesn't violate the constraint. This is your approximation set. In this case, you are inflating until you touch it, basically. And then we have an algorithm. You choose an N and you choose an R. You sample the uncertainty. For each value of the uncertainty, you calculate, you have this linear inequality. You calculate the gamma. So you have N gamma values of gamma. And then you choose not the largest one, but the 1 plus R smallest value. Not the smallest one. I mean, if you choose the smallest one, you will not have any violation. You allow R violations. So you allow that R of this radii violate the constraint. If you do this, the gamma that you get, so this notation is a notation taken for order statistics. This means you order the vector gamma, and you take, and you leave out the first R and you take the R plus 1. And this is the theorem. The theorem is proved basically applying a scenario. Basically is that. But the point is that this, you see here in the scenario approach, you have, if I go here, something that I didn't tell you, both in the scenario approach and in the other approach, you have that the size of the variable enters explicitly. And theta is the size of the variable. Here again, and theta enters in the so-called Wapnicher-Konenkis dimension, so it enters explicitly. Here it's independent of the size. So independent of the size of the problem, you have this result. And so this is the result. This is the only theorem that basically I will show you today. What is left is how to construct this set. So how to construct this initial set. And actually you can do what you want. I mean, because the initial set can be, it should be a good candidate. So what is a natural good candidate? Is again a sample set. So you sample NS inequality, but in this case, NS doesn't have to satisfy any bound. Can be what you want. Can be, for instance, because this will give you the initial shape. So, for instance, if you know that if you are constructing an MPC problem and you know that you can deal with 200 constraints, you will use an S equal to 100. You will have 200 constraints. So it's really a parameter that you can play with, and you don't need an S doesn't have to satisfy the learning theory bound. Can be everything. It's just an initial condition, and then you can inflate this set using the other approach. And of course, if you use this, you don't have a center, but you can build a center taking the Chebyshev center or the analytic center or whatever you want. And actually, you see here, this is again the set that I showed you before. In this case, we started with 100 linear inequalities, and you have the red one. This is the approximation, and then we apply the probabilistic scaling, and we get gamma less than 1. So in this case, to guarantee that you are inside, I don't remember epsilon here, I think it was 0.05. To guarantee that this is inside, you have to reduce its dimension, because we took very, very few samples. Actually, when you see it, you see that already the first one was inside, but you cannot guarantee, you cannot say anything. Or the green one, you can say that with high probability, this is really inside. Of course, if you take more samples, you have an initial set which is smaller. In this case, you inflate it. Look what happens if you take the number of, if you take the number of samples given from the first theorem that I gave you. The learning theory theorem. You get a set which is really, really small. And by the way, this has 52,000 linear inequalities for this very simple example. And to plot these, we had to prune the set, otherwise the MATLAB went out of memory. So it took a lot of work, while this is really simple. Okay, we also played with, with other sets, more complicated, if you want, which are this kind of set. This is defined this way: a center, a shape matrix H, and a ball in the space S. So if S is equal to n theta, this is a ball in n theta, and if H is positive definite, and if this is a two-ball, you have the ellipsoid. So the classical ellipsoid belongs to this set for LP equal 2. So these are LP non-base set. If you take the same thing, but with P equal 1, you have parallelotopes, but you can have much more complicated figures. For instance, if you take S equal 10 and then theta equal 3, you are basically mapping, and P equal infinity, you're mapping a 10-dimensional hypercube down to 3 dimensions, and you get what is called a zonotop. So all these enter in this formulation, and you can compute the scaling factor also in this case in a very, very simple way. So again, you can compute the scaling factor in a absolutely simple way. So if you're given a candidate set to compute the scaling factor, you basically have a closed form formula. No matter if the set is complicated or not. Also for zonotop, the formula is very simple. What is hard is to construct the initial candidate. So this is what I gave you here is a way to compute the gamma in closed form. Mm-hmm. How you construct the initial candidate? Mm-hmm. You can construct a set again, which is guaranteed to be inside a sample set. So you take a sample set, design sample set. You take 100 constraint, you have the initial sample set, and then you build something which is inside. Maybe you can inflate it a little bit more, but in order to have a better shape, because in any case, after that, you will apply, so you will apply scaling, so you can allow some violation when you do this. And to do this, you have to solve this problem. Clearly, here you have to compute the volume. So in some cases, like ellipsoid, parallelotops, this is easy because we know that the volume will be a function of h, and you know that where h is here, the volume on an ellipsoid is just proportional to the determinant of h in this case. Again, for the parallelotop, for the zonotop, the computation is much more involved, but still you can do that. Still you can do that. And these are other examples. Here I'm computing here I'm not using zonotop, just a simple L1 with H positive definite. And here there are different cases. Again, to construct the neater set, I draw 100 points. The red one is the largest L1 SIS stands for scalable approximation sets, I forgot. In this case, gamma is less than 1 again. In this other case, the initial set was this one, the red one which is inside is this one, and you have to inflate. Same thing for the infinity norm, you have these different sets. Again, we applied this, we applied to a problem of, this is only in simulation for now, but we have a project with the agricultural department of using drones in agriculture for going in vineyards and doing operations such as spraying, and so we have to drive the drones into the vineyards. This is the initial flight above the vineyard actually, and but the key point is that we use the learning theory approach that I originally proposed, and we had 20,000 constraints. The one-norm approximation are just 100 constraints. You see here the results. The results are a little worse, but the time goes from 0.4 seconds to 0.0087 seconds. So we can fly a drone, which has different dynamics than our. The nice thing about the satellite is very slow. This is a drone is much more fast. And this is it. And so what is next? We are working on scenario with certificates. We have a paper with someone in the stochastic optimization community, where we are, which is Francesca Maggioni from the University of Bergamo, and I think you know Georg Flug, where we are using these other techniques, which is a scenario with certificate, which I didn't discuss today, in multi-stage robust optimization. We have several extensions of stochastic model predictive control. We are working together with Costantino Lago, that you all know on this. And of course, any ideas you may have on this. And to conclude, I also try to invite you to Torino the next time. I mean, I think this photo will raise some nice remembrances of Torino. So thank you very much.
Thank you, Roberto. Oh, I remember this view. Absolutely. It is in my mind.
Yeah.
Great.
You didn't need that, but...
Okay, so are there any questions, please?
Pavel made a lot of questions on the fly, but you have another one?
Pavel.
Yeah. So maybe I'm missing something, but does the shape of the SAS, as you call it, does it matter? So your ultimate goal actually is to inflate or deflate it so that the resulting set will be inside your true set with certain probability.
Yeah.
So it looks like the shape of the initial SAS, being a ellipsoid or whatever, doesn't matter.
Oh, it does a lot. Let me see. Let me see if I have this. Let me see if I can do this. Okay.
Because of complexity.
Let me stop the share. Since I'm teaching, I have a board. Let me see if I can use it. Okay, let me see. There are also questions in the chat, maybe.
Yeah, there is.
Do you have a model? Yes, we do. Okay, just ask. Okay, share screen, whiteboard. You see, no, I have a lot of connections. Okay, I could explain this without the board, but since I have it, let me try with the board. If it turns on. Okay. So do you see the board?
Not yet. No.
The whiteboard.
Yeah, now we do.
Okay. So the point is, if this is the set, and let's say that you have the initial set like this, when you increase it, maybe you end up like this. You are guaranteed, but you approximated it very, very badly. I mean, you're guaranteed that all points are inside, but you're missing a lot of points. If you start with a set which is like this, and you inflate it, also these points are all guaranteed to be, I mean, you have the guarantee that this S2 is inside X epsilon. And also in this case, you have the guarantee that S1 is inside X epsilon. So you have the guarantee for both sets, but this set is a much better approximation. So when you're solving the problem, this is the green one is much better than the other one. So you have guarantees, but you can be conservative. Still, you can be very conservative. So choosing the right set is very, very important. And actually, there is a lot of room of improvement here because I mean, you can come up with ideas. As you said, it could be every set. I mean, you don't. Okay, if I leave the pen, you don't need your set to have any properties, because at the end of the day you will inflate. Actually, you need only one property, which I overlooked. You need to guarantee that the center of the set is inside epsilon. Otherwise, if you start outside, you will get 0. But if you start, the only guarantee that you need to have is that the center of the set of this scaling is inside the region. But you can usually do that taking the uncertainty equal to 0 or something like that. But the shape of the set, you can think a lot. I mean, you can have very, very different shapes. And of course, the better you can approximate your set, the better your final result will be. So this is where there is a lot of room of improvement.
Well, but again, better in what sense? So the only thing you need is a probabilistic guarantee.
You need a probabilistic guarantee, but at the end of the day, you will be solving some optimization problem of this. And so the larger of the set, the smaller is the minimum.
Okay.
Yeah. Yeah, and if the set is very, very small, you can end up with unfeasible problem. I mean, yeah, if for instance, in model predictive control, you would like to have a large set in order to have more action of your controller or something like that. So this is really important.
And of course, you do not know in advance which shape is more promising.
And actually, you see also in my example, we started with an initial sample set, but the set was not parallel. I mean,
yeah.
I was hoping that the shape was somehow parallel to this ellipsoid, but the shape was sort of perpendicular. I don't know why. I mean, this is just what we got in our example. So if you could find a way, maybe I don't know, I was thinking maybe doing some random, this is, no, I was looking at some recent paper of yours, and when you do random samples in polyton, in sets where you do these hit and run methods. And so if there was a way to check, for instance, if you're touching the boundary of this x epsilon, maybe you could use that to construct the initial set. I don't know if you see what I mean. Let me try to explain again, since I have this whiteboard. So these are ideas. But let's say that you have this ugly set here. This is x epsilon. Maybe you could indeed start from a point, draw a direction and find this other point, draw another direction and find this point. And
hit and run.
Hit and run, and then construct the convex hull of all these. This maybe is a better approximation. It just came to mind at this instant. I mean, I never thought about that. This is stimulated by your question. But maybe this is something that we could discuss. Because you need a boundary oracle of a probabilistic set, which is something that I don't know how to do this. Because you have to you need a boundary oracle of the change constraint set. But if you have that, even an approximate one, because at the end of the day, this is the initial, I mean, you don't need any guarantees. It's just the initial approximation, and then maybe you can inflate it or deflate it a little bit. So in principle, even if you have something which is not perfect, like the one that I'm depicting in pink, like you go here, and then maybe you go here, and then maybe you violate a bit, you still maybe you will have a shape that when it is reshaped is capturing the true shape better. Yeah, okay. This is something we can discuss, maybe.
I got it. And Boris, may I ask you the last question?
Yes. No.
I swear, the last one. So it is somehow related to the previous one. So if you use NS samples to shape the initial set, which you then inflate or deflate.
Yeah.
So why don't you use a very few constraints? So that then you have to shrink the set for sure, because for a small number of initial constraints, the set will be big.
Yeah, I don't know. The idea was that if you take more constraints, maybe you're reconstructing the shape better.
Yeah.
But I mean, I don't know. Actually, I really don't know what is better. I have no. I mean, in practice, you can use what you want. And
so perhaps with the large amount of initial constraints, the shape of SAS will resemble somehow the shape of the actual set.
Yeah, actually, we resemble the set of robust constraint. The probabilistic, the change constraint one is larger. The robust is where all are satisfied. But one point you can do, and actually this is what you can do, is you do not, if you take NS constraints, then you can leave out the worst R in order to maybe better approximate again. So to have something like you were doing in the ellipsoid, that you take all constraints but so the approaches that you've been using for constructing the ellipsoid containing points, these kind of ideas can be used. Maybe not with ellipsoid, with other stuff, but from that point of view, there is a lot of room of improvements. I mean, and then the procedures is really simple, and you can apply it. We have a work submitted to the CDC where we apply this to neural network. I mean, a similar approach to neural networks where you want to quantify the uncertainty in a neural network. So you have design, you have X and Y, so observations. You design, let's say, some regressor based on these observations. And then you want to say, how good is this regressor? So to quantify the uncertainty. You can do this taking other samples and observing and applying some scaling procedure. I can send you the paper.
Okay, thanks. I'm finished. Sorry. Yeah.
Okay. Other questions, please.
Okay, I have a couple of questions.
Okay, Andre.
Yes, first of all, what is like typical dimension of the design parameter in such problems? Is it low or not?
Usually, okay, the problems that we dealt with is not, okay. If you think about MPC, maybe you have 5 states, but then you have a time horizon of 10, so it's already 50, so it's around, it can be less than 50, let's say, generally.
Okay. And then when you construct approximation by Monte Carlo of the set X epsilon, when you take a lot of samples, what do you know about direction, like support hyperplane, normal
okay.
How these are distributed? Yes.
Procedure.
How do you get it bounded?
This is a very good question. I don't have idea. In our approach, we just take samples and you have points. I mean, we don't need directions. So
it's typically like more or less uniform. It appears to be uniform and bounded.
Yeah. Okay. But the point is, you have. I mean, here we are not taking sample of X. We are taking samples of theta. Sorry, we are taking sample of W. And from these, we have linear inequalities.
Yes, so this linear inequalities has to be bounded at least.
Yes.
So the set has to be bounded.
Actually, you don't need the set to be bounded because do you need the set to be bounded? No, actually not, because you have some probability, so you can. I'm not sure. I think I have to think about that, but I think you can assume. Okay, if you assume that the set is bounded, is better. But
and the final question: this function, defining the constraints, is like continuous on the parameters.
On W, measurable is sufficient to be measurable. And actually, you can write the same approach where instead of linear inequalities, you have a general function f. The point is when you compute the scaling, it's much more complicated because you have to check when you're evaluating some inequality which is not linear. So it becomes harder to compute the scaling, but the whole theory still holds for every possible. I mean, it could be circles, for instance, instead of linear. So there are cases where you can do that. We decided to concentrate on linear inequalities because it's much simpler to describe, to have nice pictures, to have these sets. And also because this nose convexity, you already have it for linear inequalities. You don't need the strain sets. I mean, even for linear inequalities, you end up with this very potato-shaped set.
Okay, thank you.
Okay. Any other questions, please?
I have questions.
Wow.
Yes, you're welcome.
Sounds great.
Thank you for your talk. I have a question about the violation parameter.
Yeah.
How do you take into account the value of the violation parameter when you construct inner approximations of the chance constraints?
Very good question. Let me show you. Actually, epsilon, which is the violation parameter, is a parameter that enters in all the bounds that I derive, enters in the construction of the bound, like here. In the linear theory, you see you have this dependence, which is basically 1 over epsilon. So it's the number of samples increases linearly with respect to 1 over epsilon. So the smaller is epsilon. So if you take epsilon 10 times smaller, you need 10 times more samples. And also here, let me see, in the scaling approach, epsilon enters in the same way. You see, enters the number of samples that you need depends linearly over 1 over epsilon. Okay, and while the dependence on delta is logarithmic. So if you have a smaller epsilon, you need more samples to construct your violation. But when you're doing chance constraint, usually you don't want epsilon too small. I mean, you allow a violation of 5% usually. So epsilon 0.05 is okay. Which means that basically you are multiplying the other part of the bound by 20. 1 over 0.05. So
okay. Thank you. Can I continue?
Yes, please. Sorry, I interrupted you.
Is it possible that in such approach you can miss some solutions if epsilon is about 500 maybe? As I understood, your technique depends on epsilon only in the sense that you choose the sample size.
Exactly.
That is, you can guarantee. Can you guarantee that this approximation is an inner approximations for the chance constraint for any epsilon for large enough value of n?
Exactly.
Okay, it's interesting. It's interesting.
So your question is that you can miss. Actually, yes. The point is, let's say that you choose, because there is this second parameter, which is delta. That's where you miss. I mean, This is a randomized technique. Every time you run it, if you run it 10 times, you will have 10 different answers, because you will consider 10 different values, 10 different set of samples. And so your approximation will be different. Your solution, in this case, for instance, the radius gamma will be different 10 times. And so you have each time a probability of missing, of doing something wrong. Or the probability that the result that you give is not correct. And this probability is captured by the delta. So the delta is the probability of giving the wrong answer somehow. But then the nice things of all these approaches, also the approaches, original approaches that we had with Boris and Pavel and Sergei and Anton, is that this delta enters under the logarithm. So you can take delta, for instance, 10 to the minus 6, which means that you will have a probability over 1,000,000. So if you run your algorithm 1,000,000 times, one time in probability, you will get a result which is completely wrong. But choosing delta very, very small is not a problem, because it enters in the logarithm. So you can be what is called almost sure that your answer is okay. But indeed, you may miss something.
Okay, thank you. It's very interesting result. Where can I read the proof of this theorem?
I can send you the paper. I can send you the paper. Send me an email, I will send you the paper. Or if you want to read the whole story, you can ask Pavel to send you a copy of my book.
Oh, thank you.
He should have one in his office. You should.
Thank you.
Excellent. Are there more questions?
So it was so nice, really. I was so happy to be here.
Fabrizio, thanks. Thanks for your very clear and very informative and inspiring talk. And thank you for the pleasure you delivered to us and all these memories arose very good. So I do hope to see you again at our seminar, and maybe in better times and the future in Moscow. Personally, it will be great. So thank you
I really
again.
hope so, yeah.
Good.
And of course, if you have comments, ideas, just send me an email. We can discuss. I mean, collaborating with you is always so nice. And
thanks, Fabrizio.
thank you.
Thanks to everybody. We'll meet the next Tuesday. Bye.
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 Bye. Thank you very much.
Bye.
Fabrizio.
Okay, thanks a lot.